Hello students, now welcome back with the Schrodinger space wave equation once again. This time we will discuss and derive the Schrodinger's equation and which will be time independent. What we have done in the starting we have done this Schrodinger's wave equation which was time dependent. So we have derived this time dependent Schrodinger's wave equation. We started with this equation, what was psi xt equal to a exponential minus iota upon h cross et minus px. You remember that we have differentiated this equation with respect to time. We have differentiated this equation with respect to x also two times. One with respect to t time, with respect to differentiated by t, we got this energy operator, where is differentiating with respect to x, then we have got this particular piece x square, or we have got the one time differentiation by with respect to x, we have got this particular momentum operator. So one time with respect to time we got E, one time with respect to x we got px, two times we got px square, and then we put this value here in E equal to px square by 2m plus v, and we got this particular equation which is Schrodinger time dependent because t is there, one dimensional equation. Then since this was dependent only in that x, and then for the next time what we have done, that not only x, we can take it in the direction of y and z together. So for all these three x, y and z, taking considering all these three dimensions, we got this equation. Here del square by del x square y square, this one is del operator, Laplacian operator also, not del, square of del. So this is also Laplacian operation, and this equation we have derived in the last class, which was Schrodinger's three-dimensional time-dependent equation. So now it should be very much clear that we have derived time-dependent Schrodinger equation. Now moving to the next choice, which is the time-independent Schrodinger equation, and we are here. So there are a variety of cases that where the potential energy of the particle may not be a function of time, and it will be the one of the major equation which we will discuss in the next lecture, when I will tell you the one-dimensional potential box as an application of the Schrodinger equation. So this, suppose potential energy is not time dependent. So what we can do, we can take potential energy only uh, time independent. Then the psi, which was the function of x and t initially, we can take it also in the psi which is function of x only, not the t part. And that is why we can remove this t part from here to derive time independent equation. How to remove this time dependent part here? So we proceed further. Let us this psi xt. Now psi xt we have taken earlier also. The psi xt was the function of something else. I can tell you that we have taken this psi xt as this one once we derive this formula. I just want to tell everybody that psi xt is equal to a exponential. Now there are the two terms. One term is the time dependent, that was a minus e iota upon h cross and et. Second one is the x dependent, maybe r dependent if you are discussing the three dimensional. So we can remove here. This whole quantity is time dependent, but this quantity px into x, we can take it as x dependent quantity. So what we can do, we can divide, or we can take this psi xt as two part. One part which is x dependent, second part which is t dependent. And to do this here, what we are doing here, to do this here, what we can do, here is the part, here is my equation. So what I can do, I can take the psi xt as the x part, and I am considering it psi x. This is important for us. And the remaining part is exponential minus iota upon h cross et. And from this equation, actually, you can divide the psi xt as a part of time and as a part of x. Now, what the meaning is that? So here, the psi axis, this contain a and the x part. So now this psi xt we will replace there. So time, we know this time dependent one dimensional Schrodinger equation was there, which we have derived. Now this vxt was there. This was a potential which depended on x and t both. Now we can take it because in my particle is, or the problem is in this way, that there is no time. So I can write vxt as vx because this is time independent. So if I replace this vxt as a vx, then I have to replace this psi xt by my psi x and exponential minus iota upon h cross et. So what I am going to do, I am replacing this vxt as a vx and psi xt from this particular equation. Now what will happen? Here if you replace psi xt with this equation, you are differentiating with respect to t. Okay, you are differentiating psi xt with respect to t. Next, here you are differentiating psi xt with respect to x two times, and obviously psi xt you can write there only. So what we can do, I am replacing now psi xt. Look there, I psi xt. So what I will do, I will actually differentiate psi xt with respect to t. Now what will happen this side? For if you differentiate this equation with respect to t, your this quantity will be constant because it is time independent. But this quantity will definitely differentiate with respect to t. So the differentiation of exponential minus iota upon h cross et will result you once again exponential minus iota upon h cross et, but with the additional quantity multiplied by minus iota h cross e, which you can see here, minus iota upon h cross e. And the all quantities in iota h cross del psi x will be constant, exponential minus iota upon h cross et the same. So this equation, which this part is from the differentiating with respect to t of this particular psi xt. Now if you differentiate this equation with respect to x two times by x, so this quantity will be constant because this is time part. In the initial, this part was constant, now this part is constant. And the rest part x, the dependent, so you can directly write del square psi x by del x square. And that is what happening here. I'm writing here del square by del x square, and this is my psi xt. From this, I can say this exponential minus iota upon h cross et is a constant which can be taken out. So there will only remaining part del square psi x by del x square. Similarly, this vxt I have replaced by vx and psi x exponential minus iota et. Now if you can look here, this exponential minus iota h cross upon et is again once again there, and here is a constant. So you can take it out from right side. So right hand side you can take it out here because this is again independent from there. So what will happen? Minus h cross square by 2m. This quantity will be remain here because this is differentiated with respect to x. This quantity will be vx, psi x will be there, and this is what the time part in the right hand side. In the left hand side, you will have this particular quantity again written here, and that quantity exponential. The time part in the left hand side and right hand side will be cancelled out. And hence, since the time part will be cancelled out, so what you can see, this e psi x is equal to minus h cross square by 2m del square psi x by del x square plus vx psi x. And in this equation, there is no time. So this equation get the time independence. Any component which is related to time get cancelled out. Hence, if you rearrange all these terms, then we can write del square by del square psi by del x square plus 2m upon h cross. I'm just taking this part here. So this e minus v will be there and psi x. And this equation is named as Schrodinger one-dimensional time independent equation. This is time independent. We derived in the yesterday's class that was time dependent. If you can now convert this equation in the three-dimensional also, so what we can do, this is what in the, if suppose now the next part, this Vx, the free particle, I told you the particle is free, there will be no potential, so you can take this Vx equal to 0, and hence we have this Vx equal to 0 here. So you can write, sorry, so you can, what you can do, you can write here that yes, my Vx will be 0, so this part will be 0, so only remaining this part and 2m e upon h cross square psi x, and that will be my one-dimensional time independent Schrodinger equation if the particle is free. I'll take this particular equation in my application of Schrodinger equation as a one-dimensional box. For three-dimensional case, this del square by del x square, as previously we have told you, the del square by del x square now will contain the y term and a z term also, which is a Laplacian. So you can write del square psi r plus 2m upon h cross square. Now, v is a function of not of x, because in one dimension it was a function of x. So now you can take this v is a function of x, y, and z. You can take it r also. So e minus vr psi r equal to 0. And this is known as Schrodinger three-dimensional time independent wave equation. And once again, the particle is free, then you can take Vr equal to 0, and it will be this equation, which is time independent Schrodinger three-dimensional equation for a free particle. I hope this is very simple. Thank you.